Hey guys, welcome back to another lecture video for Chem 115. In the previous lecture video, we learned what rate laws are and how differing the concentration of reactants can alter the rate of reaction at the same temperature. In this lecture video, we will learn how to determine the rate law, which includes the order of reaction, or the exponent in the rate law, as well as the rate constant K from experimental data. Overall, this technique is known as method of initial rates. So let's go ahead and get started. So method of initial rates is an experimental technique that essentially gathers kinetic data that can be used to help us determine the rate law for a given chemical reaction. And so the first step, if you will, of this technique is to run the reaction several times and making sure that the reaction is at the same temperature. And so it's important that the reactions are all ran at the same temperature to ensure that the calculated value for the rate constant K stays the same. The only thing that changes per each trial is the initial concentration of the reactants. For each trial, what we're going to do is we're going to differ the initial concentration of reactants, making sure that, for example, one reactant is lower concentration than the other, and then in another experiment, perhaps we'll switch it around, and the list continues. And so by running the reaction with different initial concentrations, we can go ahead and observe how changes in initial concentrations can alter the initial rate of reaction. And that'll give us a clue on the orders of reaction, which will enable us to write a complete rate law for that chemical reaction that's being ran. And so after the kinetic data is recorded from running the reaction multiple times, the initial rate of the reaction can be determined by calculating the slope at time zero. And so once you have both of these pieces, then you can go ahead and analyze how the rate of reaction changes as the concentration changes. And from there, we can go ahead and determine the order of reaction with respect to each reactant. And finally, write the complete rate law, which includes the calculated value for the rate constant K. And so you guys will not be doing this. It's impossible for you guys to collect this data in a test type setting. And so typically the kinetic data is going to be given to you, and all you need to do is analyze the data that's provided to determine the order of reaction, the rate constant K, and finally write a complete rate law. So we're going to go ahead and go through a few examples that helps solidify or helps you understand and how to perform this specific calculation. And so here we have a very specific reaction in which we have 2 moles of mercury 2 chloride reacting with 1 mole of oxalate. And that's going to produce 2 moles of chloride ion, 2 moles of carbon dioxide, and 1 mole of mercury 1 chloride. And so whenever you're trying to determine the rate law for any given chemical reaction, you don't really care about the products. What we're going to focus on is simply the rate law with respect to the reactants. Now, I do want to note that unlike relative rates, method of initial rates, writing the rate law, if you will, does not utilize the coefficients of the reactants in a balanced chemical equation. So never ever use the coefficients of a balanced chemical reaction to determine the orders of reaction, which is M and N. Sometimes your calculated value for M and N will reflect the coefficient, but that's just born out of a coincidence. And so for you to determine the order of reaction M and N, it must come from kinetic data, experimental data. Now, to write a complete rate law for this specific reaction, we essentially need to solve for two pieces. One, the rate constant K, and two, the orders of reaction with respect to their reactant. And so to do this, we're going to go ahead and look at the kinetic data that's given. So much like what I mentioned in the previous lecture slide, method of initial rates requires that multiple trials be done. So here we have trial 1, trial 2, and trial 3. And so the initial concentration of mercury 2 chloride, and we know that it's initial concentration because here we have this 0 or this naught. So this notation lets us know that we're talking about initial concentration at time 0. And so the initial concentration for trial 1 is 0.105 molar, which is a lot less than, which is less than the initial concentration for oxalate. And for trial 2, notice that the initial concentration changes again. So here in this case, we're doubling the concentration of oxalate. And we're going to, and by doubling the concentration of oxalate, how would it affect the initial rate of reaction? And so for trial 3, notice that the initial concentration of oxalate stays the same, but here in between trial 2 and trial 3, it looks like the initial concentration of mercury 2 chloride was cut in half. And so how does cutting the concentration in half affect the rate of reaction? All right, so that's the analysis portion. All right, and so to ensure precision on how to calculate the orders of reaction, we're going to go ahead and kind of build up our foundation on how to perform this type of reaction. And the first thing that we need to realize is that the initial rate or the rate of reaction is proportional between experiment 1, 2, and 3. And so we can go ahead and write a relationship that allows us to understand that the initial rate of reaction or the rate of reaction for trial 1 is proportional to that of trial 2, which is proportional to that of trial 3. Okay. And by making these statements, we can start creating ratios. So for example, we can create a ratio specifically to analyze how the rate of reaction changes between trial 1 and trial 2. And when we're writing these two trials as a ratio, we can go ahead and write it as the rate of reaction for trial 1 is equal to the rate of reaction for trial 2. Now, it doesn't have to be set up this way. If you guys want to put 2 at the top and 1 at the bottom, you'll still get the same answer. And so just for consistency, I'm just going to go ahead and put rate of trial 1 at the top and rate of trial 2 at the bottom. And so what that allows us to do, it allows us to expand the definition of the initial rate. It allows us to expand the definition of this rate by using the rate law. And so what do I mean by that? So the rate law for trial 1 is equal to the rate constant K times this by the concentration of mercury 2 chloride raised to the m power times this by the concentration of oxalate raised to the n power. Okay, And so this is the rate law for trial 1. And so this is actually the same rate law for trial 2, right? So remember, what we're trying to do is we're trying to determine the rate law. So what we're doing essentially is we are using this statement, and all we're saying is that this initial rate is either for trial 1 or for trial 2 or for trial 3. Okay. All right. So now that we have this ratio between the initial rate of reaction and that of the rate law, we can go ahead and start putting numbers in. Okay. And so once we have this equation set up, we're going to go ahead and put in the initial rate of 1 as 1.8 times 10 to the negative 5 molar per minute. And the rate of 2 from experiment 2 is going to be 7.1 times 10 to the negative 5 molarity per minute. Okay, and so the initial rate of 1 is 1.8 times 10 to the negative 5. Okay, molarity per minute. And for experiment 2, that's 7.1 times 10 to the negative 5. Molarity per minute. Okay. So this was the rate for experiment 1, and this is the rate for experiment 2. And so, you know, maybe I will just copy this down. Give me a second. Okay. And so if you guys look at this part right here on the right hand side, notice that the k's will cancel out. Okay, and so remember, this is being ran at the same temperature, so the rate constant k should be the same, and therefore they can cancel out automatically. And so the next thing that you want to do is you want to plug in the concentration of mercury 2 chloride and oxalate from trial 1 and trial 2. Okay. And so if you notice, the initial concentration for trial 1, I'm going to erase this because that's representing trial 1, is going to be 0.105. Okay. And so if you look at the initial concentration for trial 2, it's also the same. So this is 0.105. And so if you look at oxalate for trial 1, it's going to be 0.150, or I'm sorry, 0.15. And then for trial 2, it's going to be 0.30. Okay. And so what we've done is we've substituted the initial rate based on what the kinetic data is telling us, and we've substituted the concentration based on what the kinetic data is telling us. And so this is cool because this allows us to cancel another term out. So notice that here we have 0.105, 0.105. If you take the ratio of these two, this is going to cancel out, leaving us with simply this value. And let me see if I can duplicate this so I don't have to write it again. And this value. Okay. All right. So that makes the equation a lot easier. It shortens it up. And this enables us to calculate only one variable, which is n, right? And so if the concentration of mercury 2 chloride is not the same, then there's no way that this piece and this piece can cancel out. But since the initial concentrations are the same, we can go ahead and cancel out this whole term, which cancels out the m. Okay. And so if we cannot cancel this out, we're stuck with solving for two variables. All right, so now that we have canceled out one variable m, leaving us with just n to solve, we can go ahead and start reducing our values by plugging things into the calculator. And so here I'm going to take 1.8 times 10 to the negative 5, and I'm going to go ahead and divide that by 7.1 times 10 to the negative 5, which is going to be 2.5 times 10 to the negative 1, or 0.25. And I'm rounding just 2 sig figs. And so in this case, the units will cancel, so this is unitless. And so when you're trying to gather this term, what you can do is you can factor out the n. So that way all you get is 0.15, divide this by 0.30, raised to the n power. And so if you plug that into your calculator, 0.15 divided by 0.30, that's going to give us 0.5. So here we have 0.25 is equal to 0.50 raised to the n power. Now at this point, to solve for n, what you want to do is you want to take the log of both sides. And so here, we're going to take the log of 0.25, which is equal to the log of 0.50 n. The reason why we're using the log property is because the log property enables us to take this exponent and put it in front. And so what we get is log of 0.25 over n times this by the log of 0.50. Okay. And so then to solve for n, which is the variable that we're looking for, we can go ahead and divide both sides by log of 0.5. And so when you're putting this in the calculator, you're going to put log of 0.25 parentheses, and then press enter, and then that's going to give us negative 0.60, and then you're going to divide that by whatever the log is of 0.5. Okay. And so when you put this in your calculator, the value for n is equal to 2. And so there's one way that you guys can check if this makes sense. So you can go ahead and plug in n right into here. So if you put in 0.50 squared in your calculator, does that equal to 0.25? And the answer is yes. And so that's how you know that you performed this calculation correctly, when you're able to take this answer and plug it back into this variable. And so 0.50 squared is equal to 0.25. And so by performing this technique, we just now determined one of the orders of a reaction, which is n. So n is equal to 2. And so we can go ahead and update our rate law such that the rate of this reaction is equal to rate constant K times this by the concentration of HgCl2 raised to the m power. Remember that we still have not yet determined what the value of m is, so we're going to leave that alone. And then this is times that by the concentration of, I believe this was oxalate, because this oxalate is pertaining to the N. So here we have C2O4, -2. And now that we know the value for N, which is 2, we're just going to go ahead and put a 2 in front of it. Or I'm sorry, not in front of it, but we're going to put 2 as the exponent for N. So this is telling us that oxalate follows second order kinetics. And so we're not done yet. We need to figure out what M is, and then we also need to figure out what K is. But for us to figure out K, we need to solve for M. And so we're going to go back and look at the experimental data, and we're going to choose 2 experiments that will allow us to cancel N because we already found it. And by canceling out this whole term, and by canceling out oxalate, we'll be left with mercury 2 chloride, the concentration of mercury 2 chloride, and M. And M is what we need. Okay. And so if you look at experiment 2 and 3, I want you guys to notice that the initial concentration of oxalate is the same. So if you divide both of these, this is going to essentially cancel out, leaving you with mercury 2 chloride so leaving you guys with mercury 2 chloride, which will enable you guys to solve for M. And so we're going to go ahead and redo the same procedure that we did. However, we're just going to create ratios between experiment 2 and experiment 3. Okay. And remember, we're going to expand this rate law to include the reactants, the rate constant K, and the orders of reaction. So instead of writing it, I think I'm just going to copy and paste again. Sorry for cheating, guys. I just don't want to write this over and over and over again. So I will copy this, okay, and paste this. All right. And so basically what I've done is I've expanded the definition for the rate law to include rate constant K, M, and N. Okay. So now that I have my mathematical expression, I'm simply going to substitute the initial rates for experiment 2 and experiment 3. So the initial rate for experiment 2 is 7.1 times 10 to negative 5, and then the initial rate for 3 is 3.5 times 10 to negative 5. So here I have 7.1 times 10 to negative 5, and then I automatically forgot 3.5 times 10 to negative 5. Okay, molarity per minute. Okay, and so we know that the rate constant K is going to be the same if we're running this experiment under the same temperature, so we can go ahead and cancel that for now. So that's going to leave us with just mercury 2 chloride and oxalate. And so what we're going to do is we're going to substitute. Let me just copy this. Okay. So we're going to go ahead and substitute the concentrations with their actual value with respect to experiment 2 and experiment 3. And so for experiment 2, for mercury 2 chloride, I have 0.105 and 0.052. Okay, so 0.105 and I forgot it, 0.052. Okay. And so for N, for oxalate, notice that's 0.30, 0.30. Now, if you guys wanted to replace N with its actual value, since we already calculated it, you guys can. It's not really necessary, but if we plug it in, we can still cancel it, right? And so our what we're left over with is just this term and this term. And so we can go ahead and start reducing them so that our calculations just look easier on the eye. So we have 7.1 times 10 to the negative 5. Divide that by 3.5 times 10 to the negative 5. And so what I get is approximately 2.0. Okay, and remember the units will cancel, so this is just unitless. And then I'm going to go ahead and factor out the m, so I have 0.105 over 0.052 m. Okay. So if I plug that in, I get let's see here, 0.105, divide that by 0.052, and then that's going to be 2. Okay, and so this 2 is still raised to the m power. Now you guys can go ahead and do the logarithm, where you guys can think about this rationally. What exponent will allow 2 to become a 2? Okay, and so the answer to that question is 1. And so if you have 2.0 to the first power, that's just going to be 2, making that statement true. Now, if you guys wanted to go through the whole gamut with the logs, you guys can. And so here, I'm going to go ahead and take the log of both sides. So log of 2.0 is equal to log of 2.0 raised to the power of m. And so now that I have logged both sides, that enables me to move the exponent m to the very front. And I'll just get log of 2.0 is equal to m times log of 2.0. And then I'm going to go ahead and divide both sides by log of 2.0. Okay. And so that's going to cancel each other out. And if you plug this into your calculator, the answer will be 1. So therefore, the value of m is equal to 1. All right, so now that we've solved for m and n, we're going to go ahead and update our rate law such that the rate of the reaction is equal to rate constant k. Remember, we still have not yet solved for k, times this by mercury 2 chloride raised to the first power. So remember, m is connected to mercury 2 chloride, times this by the concentration of oxalate raised to the second power. Remember, this was the value for n. Okay, and so this rate law is not yet complete. The last thing that we need to solve for is k, and we need to determine its units as well. So we need to figure out the value, and we need to figure out the units for k. Okay. And so what we've done so far is figured out that oxalate follows second order kinetics, and mercury 2 chloride follows first order kinetics, and that the sum or the overall order of reaction is going to be third order. Okay. All right, now to determine the value for k, what we're going to do is we're going to choose one experiment or one trial. So it doesn't matter which trial you use, you guys will be able to get the same answer if this was ran under the same temperature. But you guys can use any of these trials, and all you're going to do is plug in the concentration and the initial rate into that rate law. And by doing so, you'll only have k as your variable. Okay, and so I'm just going to go ahead and choose experiment 1. You guys can do this for experiment 2 and experiment 3, and your answer should be the same that I get for experiment 1. So in other words, I'm going to plug in 0.105 for mercury 2 chloride and 0.15 for oxalate. And the initial rate that I'm going to be using is 1.8 times 10 to the negative 5. Okay. And so to find k, or the rate constant k, I'm going to go ahead and just copy this real quick, because I'm going to use this incomplete rate law as a backbone, if you will, to plug in my values. Okay. The initial rate of reaction, and I'm going to be using experiment number 1. You guys can use experiment number 2 or 3, it does not matter. It's going to be 1.8 times 10 to the negative 5, I believe. I forget things really easily. So 1.8 times 10 to the negative 5. And this is going to be molarity per minute, equals to rate constant K, times this by the concentration of mercury 2 chloride. And so mercury 2 chloride, if I remember correctly, was 0.105. And now this is raised to the first power because it's undergoing first order kinetics. And oxalate, oh gosh, what was oxalate? Oxalate was 0.15 molar for experiment 1. And it's undergoing second order kinetics. All right, so notice that by plugging in the values from the kinetic data, the only thing that is unsolved is K, right? And so this becomes very simple. You guys can just plug this into your calculator. So 0.105 raised to the first power is itself times this by 0.15 squared. And so that's going to be 2.3, or 2.4 if I'm rounding, times 10 to the negative 3. Okay. Now in terms of the units, remember that the bracket means molarity, right? So the bracket means concentration or molarity. And so here we have molarity to the first power, and here we have molarity to the second power. Okay. And so maybe I'll go ahead and write that out. So here I have this bracket raised to the first power, meaning that it's molarity to the first power. And then we have this bracket, whatever's inside, raised to the second power, so that means it's molarity to the second power. And so if you have molarity to the first times this by molarity to the second, all you do is you add the exponent, so that's molarity to the third. So the unit is molarity to the third power. So this is going to be times multiplied by K, and this is going to be 1.8 times 10 to the negative 5 molarity per minute. Okay. And so to solve for K, I'm just going to go ahead and divide this. And so I have 1.8 times 10 to the negative 5, divide this by 2.4 times 10 to the negative 3, molarity to the third. And then that's going to give me a rate constant value, or K, to be 7.6 times 10 to the negative 3. Now, in terms of units, let's go ahead and figure that out. So the numerator has molarity per minute, and then the denominator, remember that we divided this whole thing, is going to be molarity to the third. And so this molarity is going to cancel out with one of these, leaving this to the second power. And since this minute is in the denominator, we're going to move this down. Okay. So another way that you guys can think of this is expanding as a fraction. So molarity per minute is divide this by molarity to the third over 1. Okay, so remember that this line means division. And so when you divide fractions, you keep, you change, you flip. So you keep this, you change it to multiplication, and then you flip it. So notice that your molarity will cancel, so leaving this to the second power. And notice that your minute is in the denominator. And so the overall unit is going to be 1 over molarity second times this by per minute. Okay, so this is 1 over m squared times minute. And so this is how you determine the rate constant k for this rate law. So the last thing that we need to do is just update our rate law to include the value of k. So the complete rate law that I will definitely ask you guys on your exam is going to be 7.6 times 10 to the negative 3, 1 over molarity squared times that by minute times this by the concentration of HgCl2 raised to the first power, because it's first order kinetics, times this by the concentration of oxalate raised to the second power. So on the exam, when I ask you guys, when I give you guys a kinetic data, and from this kinetic data, I want you to determine the rate law, the complete rate law, I need you guys to figure out what K, M, and N is. Okay? And so the complete rate law for this chemical reaction at this temperature is going to be this. Okay. All right. So that's it for this lecture video. I am going to work on 2 more problems, and that's going to be on the next lecture video, but those videos are optional. I don't want to bog you guys down with videos to watch, and so if you want to watch how I solve or how I determine the rate law for 3 reactants instead of 2 reactants, as well as another problem, feel free to do so. But hopefully by me going through this singular example, you guys get a sense of how to calculate or write the rate law based on given kinetic data. All right, guys, I'll see you in the next lecture video.